Okay, we're going to talk about a new form of transcendental functions called the hyperbolic functions. And actually, hyperbolic functions are formed by taking combinations of exponential functions. And they actually can be used in computing the tension on a cable that's supported by two ends, like the electrical cable supported by two poles or something like that. And they also play a role in solving differential equations. Now, hyperbolic functions have an even and an odd part. So let me just show you. If you wanted the function f of x, you could actually write this function using two pieces. You could write it as f of x plus f of minus x over 2, and then plus f of x minus f of minus x over 2. And actually, if you simplified this, you would find that it actually equals f of x. So if you take the function e to the x and write it like that, you would get e to the x plus e to the minus x over 2, and then plus e to the x minus e to the minus x over 2. And the first term of this expression actually is what we call the hyperbolic cosine, and the second term is what we call the hyperbolic sine. And so the hyperbolic cosine is actually e to the x plus e to the minus x over 2, and the graph here just shows that to graph it you just add e to the x over 2 to e to the minus x over 2, and then you get the graph. Now the hyperbolic sine is what you get when you graph when you have e to the x minus e to the minus x over 2. So that would be the hyperbolic sine. Now we also have hyperbolic tangents, and the hyperbolic tangent is simply the ratio of the hyperbolic sine to the hyperbolic cosine. So if you take the hyperbolic sine here and then divide it by the hyperbolic cosine, you actually get e to the x minus e to the minus x over e to the x plus e to the minus x. And then here's what the graph of the hyperbolic tangent will look like. And then if you wanted the hyperbolic cotangent, you would just flip it over, because the hyperbolic cotangent is the reciprocal of the hyperbolic tangent. And that represents the hyperbolic cotangent. So remember how to represent these using the e to the x and e to the minus x. Well, hyperbolic secant is just the reciprocal of hyperbolic cosine. So if you flip the hyperbolic cosine over, you get 2 over e to the x plus e to the minus x, and that's the hyperbolic secant, and here's the graph of that. And then if you flip the hyperbolic sine over, you get the hyperbolic cosecant, which would give you 2 over e to the x minus e to the minus x, and there's the graph of that one. Now here are a few hyperbolic identities. So like hyperbolic tangent is hyperbolic sine over hyperbolic cosine. Hyperbolic cotangent is just the reciprocal of that. Hyperbolic cosine squared x minus hyperbolic sine squared x equals 1. So you might see that some of these identities sort of seem similar to the trig identities, but they're not. You can't assume that they all follow the same pattern that the trig identities do, because notice here with trig we would say cosine squared plus sine squared equals 1, but here we're saying hyperbolic cosine squared minus hyperbolic sine squared is 1. Some other identities: hyperbolic sine of 2x is 2 times the hyperbolic sine of x times the hyperbolic cosine of x. Hyperbolic cosine of 2x is hyperbolic cosine squared x plus hyperbolic sine squared. Hyperbolic tangent squared is 1 minus hyperbolic secant squared. Hyperbolic cotangent squared is 1 plus hyperbolic secant squared. Hyperbolic cosine squared is hyperbolic cosine of 2x plus 1 over 2, and hyperbolic sine squared of x is hyperbolic cosine of 2x minus 1 over 2. And the derivatives, here's the derivatives, and so I'll let you view these derivatives, but these are the formulas for the derivatives of the hyperbolics where u is some function of x. So for instance, if you wanted to differentiate a function that involved a hyperbolic function, like for instance here we have hyperbolic cosine of x cubed. Well, the derivative of hyperbolic cosine would be this formula here, and that would be the hyperbolic sine of u times u prime. So we would have the hyperbolic sine of x cubed, and then we would multiply that by the derivative of x cubed, which is 3x squared. And then here I have hyperbolic secant of u, so where u is 5x squared minus 3x. So here's the hyperbolic secant formula here, and notice it's actually going to be minus, so here's the minus, there's the minus, hyperbolic secant u, hyperbolic tangent u. So there's the hyperbolic secant of u, and there's the hyperbolic tangent of u. But then remember, we have to multiply by the derivative of u with respect to x. So that would be the derivative of 5x squared minus 3x. And so that's where the 10x minus 3 comes from, because we have to multiply by that as well. Okay, so that's derivatives, and you can just read the other formulas if you want to, or write them down, save them if you want to. Now, go ahead and look at these integral formulas, and these integral formulas actually come directly from these derivative formulas up here. So since we know that certain derivatives, we can get certain integrals. So we know if we integrate hyperbolic cosine of u, we'll get hyperbolic sine of u plus a constant, and so forth. So anyway, here's all the formulas. You can pause the video and read through these formulas. I'm just going to go ahead and work a couple of examples of integrals. So down here I have x times the hyperbolic cosine squared of x squared du. That should actually say dx. But anyway, so what you can do here is if you let u equal x squared, then du would be 2x dx. So what I can do is I can multiply on the inside by 2. That way I have 2x dx, and that is my du. Now, by multiplying the inside by 2, I had to multiply the outside by a half, so that's where the half came from. Okay, so now the 2x dx is the du, but now this hyperbolic cosine squared of x squared is hyperbolic cosine squared of u. And if you go back up here and look, here you see the formula here for hyperbolic cosine squared of u. That would be minus the hyperbolic cotangent of u. So we would have a minus, and then we have the 1/2 because we had to put the half there to manipulate it. Cotangent, hyperbolic cotangent of u plus a constant. And then the last step, go ahead and replace u with the substitution that we used, x squared. So we get minus 1/2 times the hyperbolic cotangent of x squared plus c. Now the next one doesn't really require any manipulation. Here I have the hyperbolic cosine of tangent x. So here what I can do is let u equal tangent x, and then du is secant squared x dx. Obviously I'd have been a world of hurt if I didn't have that secant squared x there, but since I have the secant squared x there, the secant squared x along with the dx, that part makes up the du, so I have the du. And then the hyperbolic cosine of tangent x is hyperbolic cosine of u. And then if you go up here to this formula, you can see that the hyperbolic cosine of u integrates to hyperbolic sine u. So that integral is going to be hyperbolic sine u plus a constant. And then the last step is to replace u with tangent. Okay, I've got a couple more here that we can look at. Here I have the hyperbolic cotangent of 5x. And what I'm going to do first here is I'm actually going to write this as using my identity. A while ago we saw that if you have hyperbolic cotangent, you can write that as hyperbolic cosine over hyperbolic sine. So I'm going to write this as hyperbolic cosine of 5x over hyperbolic sine of 5x. And then I can let u equal the hyperbolic sine of 5x. Then du would be hyperbolic cosine of 5x times 5 dx. And so now, since I don't have a 5 here with this, I'm going to have to multiply the numerator by 5. So multiply on the inside by 5, and then of course multiply the outside by 1/5, and then that allows me to multiply the inside by 5. So now this portion, 5 times the hyperbolic cosine of 5x dx, that's the du, and then the hyperbolic sine of 5x is u. So actually what I get is just 1/5 the integral du over u, and we know that when you integrate du over u, you just get natural log of the absolute value of u. So that's 1/5 times the natural log of the absolute value of u. And then your last step, go ahead and replace u with the substitution I used, hyperbolic sine of 5x, and you're finished. Okay? All right, now the next one here is a definite integral. So I'm going to integrate hyperbolic sine squared of x from 0 to 1. Now I don't have a formula for hyperbolic sine squared of x, so what I'm going to do is I'm going to use one of the identities. I can write the hyperbolic sine squared of x as hyperbolic cosine of 2x minus 1 over 2. And then what I'm going to do is break this up into two integrals. So I'm going to break it up into hyperbolic cosine of 2x over 2 minus 1/2. And then I'm going to factor the 1/2 out of each of those integrals. So if I factor the 1/2 out of the hyperbolic cosine of 2x over 2, that'll just give me 1/2 times the integral of hyperbolic cosine of 2x. And then go ahead and factor the 1/2 out of the minus 1/2 dx, and I just get minus 1/2 times the integral of dx. Now, that way, I didn't have to break it up, but by doing that, I can look at these individually. Now, you can integrate the hyperbolic cosine of 2x by just doing a simple substitution, but what you'll need to do is you'll need to multiply the outside by another 1/2 to make this work. So basically, I would have, to get this into the form of hyperbolic cosine of u, I'd have to put another 1/2 outside there. So I'd have 1/2 times 1/2, which is 1/4. And then when you integrate hyperbolic cosine of u, you get hyperbolic sine of u. So that would just be hyperbolic sine of 2x, and then the 1/4 out here. And then to integrate the dx, that's just going to be x. Okay, so now remember, this is a definite integral. So I'm integrating from 0 up to 1, so let's plug 1 in. So if I plug 1 in, I get 1/4 times the hyperbolic sine of 2. And then if I plug 1 in here, I get minus 1/2 times 1. And then over here, if I plug 0 in, so I plug 0 in, so I get 1/4 times the hyperbolic sine of 0. Now you'll find out that this is actually 0. And the way you can figure this out is just go back to the exponential form, the e to the x minus e to the minus x over 2. And if you plug 0 in, you'll see you get 1 minus 1 in the numerator, which is 0. So that's where I got the 0. And then, of course, the 1/2 x, plug 0 in there, you get 0. So since both these terms are 0, I just end up with these terms, which would be hyperbolic sine of 2 divided by 4 minus 1/2. And then you can get a calculator and get a decimal approximation of 0.40672. So I'm going to wrap this entire chapter up now with talking about the inverse hyperbolic functions. Believe it or not, we can actually talk about inverse hyperbolic functions. Just like when we talked about trigonometric functions, we were able to talk about inverse trigonometric functions. Well, we also have inverse hyperbolic functions that I'll talk about, and we have formulas for those as well.